Imagine a vault containing your company's most sensitive secrets, intellectual property, customer identities, and long-term strategic plans. Today, this vault is protected by RSA 2048, which seems impenetrable. However, adversaries are not trying to pick the lock today. Instead, they are engaging in harvest now, decrypt later, or HNDL. They intercept and store your encrypted traffic now, waiting for the arrival of a cryptographically relevant quantum computer, or CRQC. Once a quantum computer with sufficient qubits exists, your current encryption becomes a transparent window. For data that must remain confidential for 10, 20, or 30 years, the security failure has already happened. This is not a future problem. It is a present-day data breach in slow motion. This lecture will provide the architectural blueprint to stop this invisible countdown before the clock hits zero. The timeline for this threat is accelerating. The United States White House issued National Security Memorandum 10, mandating the transition of federal systems to quantum-resistant cryptography. Microsoft and other tech giants have already begun integrating post-quantum cryptography into their global infrastructures, targeting 2029 as a critical year for readiness. This is the quantum clock. In the context of enterprise risk management, we must align our cryptographic life cycles with these global benchmarks. If your enterprise hardware or software has a refresh cycle of 5 to 7 years, the decisions you make today will determine your vulnerability in 2030. Ignoring this shift means intentionally architecting future legacy debt that cannot be easily patched. Transitioning is not just about changing an algorithm. It is about redefining your entire security architecture to remain resilient in a post-quantum world. What is the ultimate goal of PQC migration? It is not merely replacing RSA with a new algorithm. We are aiming for crypto agility. This is the structural ability of a system to switch cryptographic primitives without requiring a massive overhaul of the infrastructure or application code. From a security architect's perspective, we must move away from static, hard-coded encryption settings and toward modular architectures that can respond to new threats in real time. In the post-quantum era, mathematical proofs of security change rapidly. NIST's CNSA 2.0 requirements emphasize that being quantum-resistant today is only the first step. Being agile enough to update tomorrow is the true defense. To achieve this agility, we need a structured roadmap that aligns with global standards and enterprise-level risk management frameworks. This lecture is designed to take you from the why to the how. We will first examine the mathematical vulnerability of RSA and ECC, specifically focusing on how Shor's algorithm renders our current public key infrastructure obsolete. Then, we will dive into the NIST-PQC standards, including ML-KEM and ML-DSA, which form the foundation of the 2026 Korean Security Guide. We will conclude with a practical 4-step migration framework: inventory, assessment, hybrid implementation, and full transition. By the end of this session, you will possess the vocabulary and the strategy needed to lead a PQC task force within your organization. Before we build the future, however, we must understand the mathematical failure of the present. The fatal impact of Shor's algorithm on RSA and ECC. Modern enterprise security is built on a foundation of mathematical hardness. RSA relies on the integer factorization problem, the fact that multiplying two 24-bit primes is easy, but finding those primes from their product is computationally impossible for classical machines. Similarly, elliptic curve cryptography, or ECC, relies on the discrete logarithm problem. For decades, we have scaled security by simply increasing key lengths, assuming that the work required for an attacker grows exponentially while the work for a legitimate user grows only cubically. This asymmetrical power dynamic is what allows us to trust TLS handshakes and digital signatures across the open internet. However, this security model assumes that every computer must follow the classical rules of binary logic. In a world where quantum bits exist, these hard problems aren't just difficult. They become fundamentally solvable in a fraction of the time. The shift we are facing is not a matter of if, but when the underlying math becomes transparent to high-performance quantum observers. But what happens when the logic of computation itself changes? This change is driven by a single mathematical breakthrough that redefined the limits of what is possible. Shor's algorithm is the definitive black swan event for the cybersecurity industry. Proposed by Peter Shor in 1994, this quantum algorithm utilizes the principles of superposition and interference to find the period of a function, which is the missing link needed to solve factorization and discrete logs. On a classical computer, breaking a 2048-bit RSA key would take trillions of years using the general number field sieve. Shor's algorithm, however, reduces this complexity from exponential to polynomial time. This means that a sufficiently powerful fault-tolerant quantum computer could potentially crack the encryption that protects our global financial systems, government secrets, and personal identities in mere hours or even minutes. This is not just a faster processor. It is a fundamental collapse of the barrier between public keys and private keys. We are moving from an era where encryption was a permanent lock to one where it has a definitive expiration date. You might wonder if symmetric encryption like AES suffers the same fate. The answer is surprisingly different. Payoff: while Shor's destroys RSA, symmetric encryption faces a different, more manageable threat. It is critical for architects to distinguish between the threats to asymmetric and symmetric cryptography. While Shor's algorithm is a total kill switch for RSA and ECC, Grover's algorithm is a degrader for symmetric ciphers like AES and hash functions like SHA-3. Grover's provides a quadratic speedup for unstructured searching. In practical terms, this means that a 128-bit AES key is reduced to only 64 bits of effective security in a quantum environment, which is well within the reach of modern brute force capabilities. However, unlike RSA, we don't need to throw away AES. By simply upgrading from AES 128 to AES 256, we maintain 128 bits of quantum-resistant security. This leads to a two-pronged migration strategy. We must replace our asymmetric infrastructure while simply strengthening our symmetric layers. Understanding this distinction is vital for prioritizing your security budget over the next 3 years. If the core algorithms are failing, we must look at where they are hiding in our current infrastructure. Teaser, the vulnerability isn't just in your code, it's in the very architecture of how your company communicates. The vulnerability of RSA and ECC isn't just a theoretical problem for researchers. It is a structural crisis for IT infrastructure. Every time you open a browser, the TLS handshake relies on these algorithms to exchange session keys. Your PKI, which manages the lifecycle of digital certificates for employees and machines, is likely rooted in RSA 4096. Digital signatures in your CI/CD pipelines, which verify that production code hasn't been tampered with, are almost certainly using ECDSA. Even your VPN gateways and identity providers, IP, utilize these protocols to establish trust. In an era of harvest now, decrypt later HNDL, attackers are already capturing this traffic, waiting for the day they can unlock it. As an architect, you must realize that every byte of data encrypted today with legacy asymmetric crypto is effectively public data in the near future. We are talking about a total erosion of the root of trust that defines modern business. Mapping these risks is one thing, but finding the hidden hard-coded secrets is where the real nightmare begins. Teaser, you might be surprised at how deeply these algorithms are buried in your legacy systems. The greatest hurdle to PQC migration isn't the new math, it's the technical debt. Over the last 20 years, cryptographic algorithms have been ossified into our systems. We see hard-coded RSA keys in legacy Java applications, proprietary hardware security modules, SSMs, that only support specific ECC curves, and third-party APIs that expect fixed-length ciphertexts. This lack of crypto agility means that many organizations cannot simply flip a switch to update their security. If your application logic is tightly coupled with 256-bit output of an ECC curve, moving to a PQC algorithm with a much larger public key will break your data schemas and network packets. This is why a thorough inventory of cryptographic assets is the first priority of the Korean Security Guide 2026. You need to identify where encryption is embedded, who owns the keys, and whether the underlying platform can even support the larger computational overhead of post-quantum math. To fight this, we need a new set of tools, and that's where the NIST-PCC standards come into play in the next chapter. Bridge, in the next chapter, we will meet the new guardians, the specific PQC algorithms that NIST has selected to replace our fallen giants. The journey to post-quantum security began with NIST's global call for proposals, moving beyond the factoring and discrete logarithm problems that underpin RSA and ECC. To ensure long-term resilience, NIST categorized candidates into 3 major mathematical families. Lattice-based cryptography is the current frontrunner, offering a balance of speed and key size. Code-based cryptography, rooted in error-correcting codes, provides a mature alternative with high confidence, though often at the cost of larger public keys. Multivariate cryptography relies on the difficulty of solving systems of nonlinear equations. In professional practice, understanding this taxonomy is critical because it determines the crypto agility strategy of your enterprise. Each family offers different security assumptions, ensuring that even if one mathematical foundation is compromised by a future breakthrough, the industry has a viable secondary defense. But among these 3 diverse families, which specific algorithm emerged as the definitive global standard for encryption? Meet ML-KEM, formerly known as Kyber, which has been finalized under the FIPS 203 standard. As an information security architect, you should view ML-KEM as the successor to RSA and elliptic curve Diffie-Hellman. Its primary role is key encapsulation, the secure exchange of symmetric keys over an untrusted channel. ML-KEM is built on the module learning with errors or ML-DSA problem. It was selected because it offers excellent performance across various platforms, from high-end servers to resource-constrained IoT devices. When you audit your enterprise applications, look for libraries that are now transitioning to FIPS 203 compliant implementations. This isn't just a minor update. It's a fundamental change in how we establish secure sessions for TLS 1.3 and beyond. In the real world, this means your future handshake protocols will look slightly different under the hood. But wait, encryption is only half the story. How do we handle the equally critical task of digital signatures and identity verification? For digital signatures, NIST has introduced ML-DSA and SLH-DSA under FIPS 204 and FIPS 205. ML-DSA, derived from the dilithium algorithm, is the primary recommendation for general-purpose signatures due to its high efficiency and relatively small signature sizes. However, for use cases requiring extreme longevity or a different security foundation, we have SLHDSA based on the spin++ design. SLHDSA is a stateless hash-based signature scheme. While it produces larger signatures and is computationally more intensive, it is incredibly robust because it relies only on the security of hash functions like SHA-3 rather than lattice math. From an engineering perspective, choosing between ML-DSA and SLHDSA requires a careful trade-off analysis of bandwidth versus security margin. Most enterprise PKI systems will likely default to ML-DSA, but SLHDSA serves as a vital break-glass alternative. This dual signature strategy ensures that our digital identities remain valid even as quantum threats evolve. But what is the underlying logic that makes these algorithms so much harder for a quantum computer to crack? To understand PQC, we must grasp the learning with errors or LWE problem. Imagine trying to solve a simple system of linear equations. This is easy for any computer. Now imagine we add a tiny bit of random noise or error to each equation. Suddenly, for a computer to find the exact secret variables, it must solve an incredibly complex problem that is equivalent to finding the shortest vector in a high-dimensional lattice grid. While Shor's algorithm can effortlessly factor large primes, it has no efficient way to navigate these noisy lattice structures. ML-KEM uses module LWE, a more efficient variant that organizes these equations into matrices over polynomial rings. This provides a level of security that scales much better than RSA. For practitioners, the takeaway is simple. We are moving from number theory involving large primes to high-dimensional geometry. This shift is what makes PQC resilient against the parallel processing power of a quantum processor. But how does this translate into the actual size and speed of our encrypted data? In the NIST-PQC standards, security is categorized into security levels 1, 3, and 5, which correspond to the computational difficulty of breaking AES 128, AES 192, and AES 256 respectively. As an architect, you understand the trade-offs. PQC is not a free upgrade. For instance, ML-KEM 768, Level 3 offers a robust security margin for most enterprise needs, but its public key is over 1,000 bytes. Contrast this with ECDH, where keys are typically only 32 to 64 bytes. This increase in key and ciphertext size can lead to fragmented packets in network protocols or increased memory overhead in embedded systems. However, the computational speed for encryption and decryption in ML-KEM is remarkably fast, often faster than traditional RSA. When planning your migration, you must balance these physical constraints against your security requirements. Choosing level 5 might seem like the safest bet, but is your infrastructure ready for the increased bandwidth? This leads us to ask, what happens if lattice-based math is one day broken? Does NIST have a plan B? Security is about defense in depth, and NIST recognizes this by maintaining round 4 candidates as backup standards. These include code-based algorithms like BIKEY and HQC. Unlike lattice-based schemes, these rely on the difficulty of decoding general linear codes, a problem studied since the 1970s. While they were not selected as the primary standards in the first wave due to larger key sizes or higher complexity, they remain active as essential alternatives. If a catastrophic vulnerability is discovered in lattice mathematics, the industry will pivot to these code-based schemes. This is the essence of crypto agility building systems that can swap out one algorithm for another without a total redesign. As we move toward 2026, the Korean security landscape is also aligning with these global benchmarks. We've established the what and the why of the new standards. Now it's time to tackle the how. In the next chapter, we will dive into the practical enterprise migration framework to transition your legacy assets to these new guardians. To survive the post-quantum transition, an enterprise must first understand its current cryptographic footprint. As a professional engineer, I emphasize that you cannot protect what you cannot see. We begin with a systematic discovery process, often referred to as a crypto asset inventory. This isn't just a list of certificates. It's a deep audit of every algorithm, key length, and protocol version currently active in your environment. We utilize automated scanning tools to inspect source code for hard-coded primitives, monitor network traffic to identify legacy TLS 1.2 or RSA-based handshakes, and query hardware security modules (ASMs) for stored secrets. This phase aligns with the NIST SP 1838 guidelines, focusing on establishing crypto agility, the ability to swap algorithms without re-engineering the entire application stack. By documenting the as-is state, we identify exactly where RSA 2048 is lurking in your legacy databases and legacy middleware. But finding the keys is only half the battle. The real complexity lies in the invisible web of dependencies that hold your infrastructure together, something we will map out in the next scene. Once we have our inventory, we must visualize the internal and external dependencies that define our security posture. This is where many enterprise migrations fail. They ignore the third-party ecosystem. Your organization likely relies on external libraries like OpenSSL or Bouncy Castle, cloud providers for key management services, KMS, and SaaS vendors who manage their own encryption. A dependency mapping exercise reveals how a single vulnerable RSA implementation in a third-party API can compromise your entire data pipeline. We must categorize these dependencies into internal control code you own, external reliance services you consume. From a technical lead's perspective, this mapping is critical for risk assessment. If your cloud provider doesn't support ML-KEM by 2026, your internal PQC readiness might be rendered useless for external communications. We are looking for quantum dead ends where hardware limitations prevent firmware updates to PQC. Knowing where the algorithms are is vital, but how do we decide which one to fix first when everything seems urgent? With thousands of assets identified, prioritization is mandatory. Not all data is created equal in the eyes of a quantum adversary. We use a prioritization matrix based on two main factors: data longevity and system criticality. This directly addresses the harvest now, decrypt later HNDL threat. If you have encrypted data with a shelf life of 20 years, such as national secrets, long-term financial records, or genomic data, it must be migrated to PQC immediately because it can be captured today and decrypted in 2029. In contrast, ephemeral session data for a low-impact web service might be lower on the list. We rank systems into 3 tiers. Tier 1 includes root CS and long-term data storage. Tier 2 covers high-traffic communication channels like VPNs. Tier 3 is for short-lived internal microservices. By applying this technical filter, you ensure that your limited budget and engineering resources are focused on the highest risk areas first. With a roadmap in hand, we must move to implementation, but jumping straight to PQC is a dangerous gamble that requires us a safety net, as we'll see in the next section. The industry consensus for the next several years is not a total replacement, but a hybrid implementation strategy. NIST and major security agencies recommend combining a classical algorithm like ECC, like 2515, with a post-quantum algorithm like ML-KEM, formerly Kyber. Why? Because while PQC is mathematically resistant to quantum attacks, it is relatively new and hasn't been battle-tested against classical cryptanalysis as much as RSA or ECC. In a hybrid setup, the security of the connection is maintained as long as either pair of the algorithms remains unbroken. This provides a safety net. If a flaw is discovered in the new ML-KEM standard, the classical ECC layer still protects the data from current threats. Furthermore, this approach helps maintain FIPS 143 compliance during the transition period, as many existing regulations still require a NIST-approved classical primitive. This best-of-both-worlds approach is the gold standard for enterprise-grade security. Theoretical safety is one thing, but how does this actually look in your server configurations and handshake protocols? Let's look at the configuration. In practice, implementing hybrid PQC often involves updating your TLS 1.3 configurations to support new named groups. For example, the industry is coalescing around X255 ML-768 for key exchange. In this scenario, during the TLS handshake, the client and server exchange both an elliptic curve Diffie-Hellman key and an ML-KEM encapsulated secret. Leading web browsers and content delivery networks have already begun shipping support for these hybrid groups. In your server configuration, you would specify these new ciphers to prioritize quantum-resistant handshakes for compatible clients while maintaining backward compatibility for older ones. This is a practical example of crypto agility in action. By enabling these settings, you are effectively neutralizing the harvest now, decrypt later threat for all new sessions. The code change is often minimal, simply adding a new algorithm identifier to your allowed list, but the architectural impact is profound. The security is undeniable, but every extra byte in the handshake carries a cost, one that could break your user experience if not measured correctly. Transitioning to PQC isn't a free lunch. There are significant performance trade-offs that architects must for. PQC algorithms, especially lattice-based ones like ML-KEM, have much larger public keys and ciphertext compared to ECC. For example, while an X255 public key is only 32 bytes, an ML-KEM 768 public key exceeds 1,000 bytes. This increased payload can lead to increased network latency, especially in environments with high-frequency handshakes or limited bandwidth. Furthermore, the CPU cycles required for key generation and encapsulation are higher, which might impact the maximum concurrent connections your load balancers can handle. In our testing, we often see a slight increase in time to first byte TTFB when hybrid handshakes are enabled. It is vital to perform stress tests on your edge devices before a full-scale rollout. You must balance the security margin against the performance budget. We've built the framework, but global standards are only half the story. We must now look at how Korea's unique security landscape and the K-PQC initiative shape our national defense in the next chapter. While NIST sets the global pace, we must look closely at the Korean landscape where the regulatory environment is shifting rapidly. The Korean Cryptographic Validation Program, known as KCMVP, is currently undergoing a massive overhaul to include PQC verification by 2026. For those of you managing public sector projects or financial infrastructure in Korea, this is not a distant concern. It is an immediate architectural requirement. The National Intelligence Service and K-PQC have emphasized that by 2026, any new cryptographic implementation within the public sector must be evaluated against quantum-resistant standards. In the field, we see this as a move toward cryptographic sovereignty, ensuring that critical domestic data remains protected against future decryption threats. This transition requires us to re-evaluate our current KCMVP-validated modules and plan for a hybrid approach where classical and PQC algorithms coexist to maintain both compatibility and future-proof security. Have you audited which of your current modules are KCMVP certified? The rules are about to change, and staying ahead of this 2026 mandate is critical for compliance. But wait, how do Korean algorithms actually differ from the NIST finalists we've discussed? In the global arena, NIST has standardized algorithms like ML-KEM, Kyber, and ML-DSA at dilithium, but the Korean cryptographic community is also advancing local candidates such as Lizard and specific variants of NTRU. From an architect's perspective, the key is understanding algorithm interoperability. While NIST standards provide global reach, local K-PQC algorithms are optimized for domestic performance requirements and specific hardware environments often used in the Korean financial sector. For instance, Lizard is a lattice-based algorithm that offers competitive performance in low-power IoT environments compared to standard Kyber. When designing your enterprise architecture, you must consider whether your system needs to support multi-algorithm flexibility. This means your cryptographic provider should be able to switch between a NIST standard dilithium for international communications and a K-PQC validated algorithm for domestic regulatory compliance. This duality is often where architects fail. They choose one and lock themselves out of the other. We must design for a world where different regions may mandate different PQC primitives. Is your system flexible enough to handle this regional divergence? This question leads us directly to the specific compliance milestones you must hit over the next few years. Timing is everything in enterprise security. The roadmap for K-PQC compliance isn't a single event but a multi-stage marathon. We are currently in the observation and pilot phase, where leading financial institutions and government agencies are running test beds with PQC-ready VPNs and PKI systems. By 2025, we expect the release of finalized domestic implementation guidelines. Then comes the 2026 milestone, the mandatory adoption for new public sector infrastructure. This includes smart city projects, cloud-based government platforms, and next-generation military communications. By 2030, the goal is full migration, where legacy RSA and ECC are phased out from all critical national infrastructure. For a technical leader, this means your 2024-2025 budget must include PQC impact assessment. If you wait until 2026 to start, you will face an impossible backlog of technical debt. Think of it as a rolling upgrade. Start with the most exposed external interfaces and move inward to your core databases. This timeline isn't just about avoiding fines, it's about closing the harvest now, decrypt later window before it's too late. But where does PQC actually sit within your modern infrastructure? It's time to talk about the architectural positioning in a zero-trust world. In modern security architecture, PQC is not just an encryption update, it is a foundational pillar of zero-trust architecture, ZTA. In a zero-trust model, identity is the new perimeter, and that identity is verified using cryptographic certificates and tokens. If your identity and access management (IAM) system relies on RSA-based JDTs or OIDC tokens, your entire trust model collapses the moment a quantum computer can forge those signatures. Therefore, PQC must be positioned at the policy enforcement point and the trust engine level. Every time a user or device requests access, the underlying handshake should ideally be protected by a PQC-ready protocol like TLS 1.3 with quantum-resistant key exchange. We must view PQC as the layer 0 of the security stack. Without it, your layer 7 policies and layer 4 firewalls are built on sand. Integrating PQC into your ZTA strategy ensures that even if a network is breached today, the session data captured by an adversary remains unreadable in the future. This is the ultimate expression of continuous verification. But how do we physically manage these new, larger PQC keys? The answer lies in the hardware that lives in your data centers and clouds. When we move from theory to physical hardware, the hardware security module HSM becomes our biggest challenge. Most legacy HSMs are optimized for the mathematical operations required by RSA and ECC. PQC algorithms like dilithium or Kyber use lattice-based math, which involves significantly larger key sizes and different computational patterns. This means your current HSM might not have the memory or the processing power to handle PQC at scale. You must begin a hardware audit immediately. Are your HSM's firmware upgradable to support NIST PQC finalists? If you are using Cloud KMS service from AWS, Azure, or Google Cloud, you need to look at their hybrid key offerings. These services allow you to wrap your keys with both a classical and a PQC layer. The process involves identifying your most sensitive keys, evaluating the HSM's support for large key storage, and testing the latency impact of these new algorithms. In many cases, a hardware refresh cycle will be necessary to meet the 2026 KCMVP performance standards. But what about the software developers? How do they write code that doesn't break every time an algorithm is updated? The final piece of the architectural puzzle is crypto agility at the code level. Hard-coding specific algorithm names like RSA 2048 into your application logic is a recipe for disaster. When NIST or K-PQC releases a new version or an algorithm is suddenly found to have a flaw, you don't want to rewrite thousands of lines of code. Instead, developers should use abstraction layers or agile crypto APIs. By utilizing libraries like OpenSSL3X with the OQS, Open Quantum Safe provider, you can refer to cryptographic functions through a generic provider interface. This allows you to swap ML-KEM 768 for a future algorithm just by changing a configuration file or a single line of provider initialization. For Java developers, using the bouncy castle PQC provider is a best practice. The goal is to decouple the business logic from the cryptographic primitives. This ensures that when the 2026 mandate hits, your transition is a configuration change, not a code rewrite. This level of agility is what separates resilient enterprises from those that will struggle to survive the quantum transition. Now that we have the global and local context, how do we put this all together into a concrete 30-day plan? That's exactly what we'll cover in the final chapter. As we conclude this lecture, let's look at the massive paradigm shift occurring in the cryptographic landscape. For decades, RSA and ECC have been the bedrock of enterprise security, relying on the hardness of integer factorization and discrete logarithms. However, with the NIST FEPS 20304 and 205 standards now finalized, we are moving toward lattice-based structures like ML-KEM and ML-DSA. This shift is not merely a technical update. It is a defensive necessity against the harvest now. Decrypt Later, HNDL. From the perspective of an information management professional engineer, you must view this transition through the lens of enterprise risk management. We are moving from a world where current encryption is a static safe vault to one where it is a ticking clock. Understanding that PQC transition requires hybrid modes, where we wrap traditional keys with quantum-resistant layers, is the first step in maintaining long-term data confidentiality and integrity across your digital infrastructure. This strategic alignment ensures that your organizational secrets remain secure even when the predicted Q-day eventually arrives. But how do we actually start this monumental task in a real enterprise environment? Let's break down the immediate practical steps. Transformation begins with a clear, actionable roadmap. Over the next 30 days, your priority is establishing cryptographic agility within your organization. Step 1. Conduct a comprehensive crypto inventory. You cannot protect what you cannot see. Identify every instance of RSA 2048 or ECC in your internal and external traffic. Step 2. Categorize your data by its longevity value. If data must remain secret for over 10 years, it is at high risk from HNDL and requires immediate PQC intervention. Step 3. Design a hybrid migration strategy. Modern security architects are already testing dual signatures and hybrid key exchange to maintain backward compatibility while adding quantum resistance. Finally, demand a PQC roadmap from your infrastructure vendors. Whether it is your cloud service provider or your hardware security module HSM manufacturer, verify their support for NIST-standardized algorithms like Kyber and Dilithium. This 30-day plan is the foundation for an enterprise that is not just compliant, but truly resilient against future compute paradigms. This completes our deep dive into PQC migration. Now, the real work of securing the next decade of digital assets begins. Your first audit tomorrow. Stay vigilant and keep refining your security architecture.